So we have our final quiz of the quarter, quiz 7, and the cover sheet, as it were, was a pile of spherical harmonics, so YLMs, up to as many as you may or may not have needed. Spoiler alert, you needed them. And then a table of Legendre polynomials. And for brevity, and in general, the Legendre polynomials are called Pn or Pl of x, even though we usually see them with a cosine instead of an x. So first question is to turn the following differential equation, partial differential equation, into a set of uncoupled ordinary differential equations. And you don't have to solve them, just find them. And the fundamental trick of doing that is separation of variables. Which is to make the assumption that in this case, I see that I'm taking derivatives of u with respect to the variables x and t. So we have u of x and t. And we can separate that solution into two factors. And I'll be uncreative as usual and say capital X of x and capital T of t. So there's a product form for the solution. And then after that, it's just plugging this in and seeing what the partial differentials give you and hopefully algebraically solving them. So I have d by dx of x and t times x equals minus k, and then two partial derivatives with respect to t of capital X and t. And we'll see how long I can keep the big serif x's and t's up. Okay, so math happens and I get variable x times function x prime t has no dependence on x, so that partial does nothing. And then minus k x t double prime. So this is the algebra step. So once I have this, after my assumption that I can separate variables, I hope that I can separate them. So I can, and I get these two equations. Actually, let's do one step at a time. This equation, x prime over x equals minus k t double prime over t. And again, the game is that if there are two of us and I pick any value out of, in this case, maybe let's say the entire real line and of x, and you pick any value of t, and we keep them hidden, and then we go 1, 2, 3, shoot. I reveal my value of x, and you reveal your value of t. No matter what they are, these two sides are equal. And so the only way that could happen is that each one independently is equal to a constant. So it's some constant, maybe that's a parameter of the problem or one of the components of the solution, but each of these has to be equal to a constant. And because there's a second derivative here, I might be tempted to call it alpha squared. That's probably a good idea. Usually what happens is with hindsight, people know to call this alpha squared or alpha times alpha minus 1 or plain old ordinary alpha. Doesn't matter what you called it. If you just put down a constant, that's fine. I'll just call it alpha to keep the notation brief. So now what we have is that each of these two sides independently is equal to alpha, which gives me the two ordinary differential equations, x variable times x prime is equal to alpha x. Don't have to bother solving it because I wasn't asked to. And then minus k t double prime equals alpha t. So that is two ordinary differential equations, and we're done. So the second problem is not a lot of math, as it turns out, but a lot of understanding what that table of spherical harmonics is and what it means to express something in terms of spherical harmonics. So in general, if I'm going to express something in terms of spherical harmonics, what I'm saying is that somewhere out there, there's an expression for f of theta and phi, which is the sum over all possible L's and all possible M's of some coefficient CLM, YLM. Okay, it turns out that we're not going to need all of them, but what we're looking for is a sum and trying to figure out what these unknown coefficients are, the amplitudes of each CLM. Okay, so we went through one of these the hard way and the easy way. The hard way is to take a whole bunch of integrals. The easy way is to just kind of squint at the table and think about how the function depends on, or how each piece depends on the kind of active ingredients of thetas and phis. And even further than that, there's just a smoking gun hint that anytime I have an e to the I phi, that would be m equals 1. And if I had like e to the I minus 4 phi, for instance, that would be m equals minus 2. And then I realize it's kind of weird. You say them YLMs, but then you write them YMLs, or at least maybe I do. So I'm looking at something here that says I'm probably going to have y equals 1 because I have a sign to the first power, trig function of the first power. And I probably have an m equals 1 too because I have e to the I 1 times phi. And then the remnants, so this is looking to me like I might be y11. And then over here, I have this left over. Okay, we'll see about the constant term, but I definitely have no phi term, and I definitely have a power of 2 theta term. So I'm probably looking at y02. And we'll see about that constant. That constant might be y00, might not be. So we'll just realize that we do have a y00 left over. Okay, so remember that sine theta, ei phi, and then cosine squared, maybe minus something, maybe not. So we'll scroll back to the table with our ghostly writing following us. And there it is. So y11 is sine theta ei phi, and y02 is cosine squared theta minus a constant. So we might still have to add y00, but we'll get to that when we get to that. And then park that back there. So now what I know, and I can write this in the following way. So I've got a first term. And the first term itself, let me just pull all of this in. So I have a minus 1 over root 4 pi. So that gives me a first term of minus 3 over root 16 pi sine theta e to the I phi. And I know that that equals C11. So we did identify that as the 1 term times whatever that is, as in I read it off the table above. And I don't have an amazing memory. I have this transcribed on notes next to me. So as per the table, y11 is negative root 3 over 16 pi sine theta ei phi. Let me sure you're howling as you watch that. You correct that. That is absolutely phi. I wrote theta. So the question is, what is C11? So honestly, just by examination, I can see that how did I get from here to here? I just got to multiply by root 3. So this is just missing a root 3 to turn the right-hand side into the left-hand side. So this is all supposed to be about the concept and not necessarily about, the math of computing overlaps. So C11, honestly, just by inspection, is equal to root 3. So first term was not that bad. So let's see about the second term. So our second term, and for this one, I think it makes a little bit more sense because, if you remember from the table, we have a 3 cosine squared minus 1 is I'm actually going to just like factor stuff out. So this is the second term from f theta phi, 1 over 4 pi And then I can factor out from both of the terms in the sum 5/2. And what I'm left over with is 3 cosine squared theta minus 1. And I know that that's the y02 term, because at this point I recognize the 3 theta squared minus 1. That was just in the table itself. Turns out we don't need a y00 to cover any extra constant. So there was a 3 cosine squared minus 1. So that is just the Legendre polynomial, the P2 actually. So this is equal to a thing that we're looking for, C20, times what I read off of the table. And what I read off of the table is 1/4 times √5 over pi, and then our happy term 3 cosine squared theta minus 1. So 3 cosine squared theta minus 1, got it on both sides. We have a √pi downstairs on both sides. Everything's looking good. We have 2 and a 4 and a 2. So the denominator actually looks all good. All that we're missing is, again, just doing this by inspection, no complicated math, no integrals over all solid angle. We have a √5 on the right-hand side, and we have a -5 on the left-hand side. So just again, by inspection, C20 is equal to -√5. And our final answer, therefore, is that f of theta and phi is equal to √3 y11 minus √5 y02. Okay, so that problem was also a little bit of a warm-up or memory jog for the last one, and this is the one that actually has some physics in it. Although the thing above it is sort of a twisted version of the heat equation. I just changed the variables, x and t, to try to hide it from you if you've seen the heat equation. So now we have a multipole expansion, and this is an actual electrostatics problem, and one that you'll probably do a couple of times, so it's good to see it again. So there's a charged sphere, and somehow I have a potential that's proportional to cosine squared. So this is some sort of non-perfect conductor insulator, and I painted a charge distribution on it at the surface. So this thing has a radius of r, and at the surface I have v naught cosine squared theta. And the question is, find the electric potential everywhere outside of the charged sphere. So finding the electric potential everywhere is essentially asking find v of r and theta. Okay. So we know two things. We know that at the surface it's given to us, and we also know that in general this is the way to solve Laplace's equation. So outside means we got no charge. This is the way to solve Laplace's equation in spherical polar coordinates. You just say, well, I know that this is equal to sum over a multipole expansion. So sum from L equals 0 to infinity of AL RL plus BL RL plus 1 times Legendre polynomial of cosine L. So that's always true. That's the solution of the Laplace equation in spherical polar coordinates. The question is just how many of those terms do we keep and what are they? And it turns out we're not going to keep too many of them. And in fact, you can probably guess which terms we're going to keep because we already solved the cosine squared thing last problem. So going about this sort of diligently, the first thing I can do is I can argue that all of these are gone aside from A0. And the reason I can argue all of them are gone is because at infinity, as r goes to infinity, the potential should be 0. Right? So as you get really far away from this, it'll look like first a dipole, then a point charge. And then as you're really far away, it should drop to 0. So that means any of these positive powers of r can't contribute. So I could have an L equals 0 term that would just be L or A naught, but I'm also free to choose a potential to be different by a constant. So I'm going to throw that away as well. And it turns out that's actually, in the solution. So I'll just say all of these are 0. So you have to go to 0 at infinity, which means no A terms. So now I map what I do know onto the terms remaining. So I know that V of r and theta evaluated at the surface is equal to sum L from 0 to infinity BL RL plus 1. It's a 1. PL cosine theta. But then I also know that's equal to V naught cosine squared theta. So, and this is true for all theta, all values of theta. We fixed r, but we didn't fix theta. So the question is honestly, how do I just express cosine squared theta in terms of Legendre polynomials? And to express cosine theta in terms of Legendre polynomials, I can go up and I can look at that table again, but we've already seen which one it is. So we need a squared. So here's our squared. So 1/2 times 3x minus 1. And then we got to get rid of that 1. So we're going to have P2. That's how we get our cosine squared. And then we're going to have some P0. That's how we get rid of that constant. So pretend I'm toggling back and forth in between the table and this little sidebar, but I'm just going to write down the answer. So I have V naught cosine squared theta is equal to, juggling a little bit, V naught times 2/3 P2 cosine theta plus 1/3, got to get rid of that 1/3, P naught cosine theta. And you can check that that's true. So the 3/2 cosine squared theta minus 1 and the 1/3, that will get me what I need. Okay. So now I can just replace that here. So I have V naught 2/3 P2, and what is dot dot dot, it's cosine theta, plus 1/3 P0, dot dot dot, that's cosine theta. And what this means is of the sum of infinity terms, L goes from 0 to infinity, we only have 2. So we only have the 0 term and we only have the 2 term, and then I can write that down. So sorry, that should also be capital R because we are evaluating this at capital R. So this has got to be equal to B naught capital R P naught dot 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 plus B2 R cubed P2 dot dot dot. And so now it just comes down to matching terms. So what's the coefficient on P naught? From the right-hand side, it's 1/3 V naught. From the left-hand side, it's B naught over R. So that means that B naught over R is equal to 1/3 V naught for matching that first term. And for matching the second term, likewise, I get B2 over R cubed is equal to 2/3 V naught. Therefore, B2 is equal to 2/3 V naught R cubed, and B naught is equal to 1/3 V naught R. And A, everything else is 0, and B, everything else is 0. So that 2 times infinity terms, we only have 2 non-zero ones that contribute. And after you do this a few times, you just kind of can look at this and read that answer off. It's like, oh, I just have a cosine squared. So I'm only going to have terms up to the second L equals 2 of the multipole expansion. So let me clean this up a little bit, and then we'll report our final answer. So we got what those 2 non-zero terms are by evaluating this at the surface of the sphere, but what we were asked for is the electric potential everywhere. So we just got to take our full multipole expansion and just put in the 2 non-vanishing terms. So this is B naught over R squared, P2, oops, sorry, mixing terms. This is B naught over R, little r, P naught cosine theta, plus B2 R cubed P2 cosine theta. We're plugging in our values for B naught and B2, V naught R over 3 little r, P naught cosine theta, which is a really fancy way of writing 1. And then B2 is 2 V naught R cubed. I'll fix that thing on the right-hand side in a second, over R cubed 3. P2 cosine theta, which is probably better to just keep calling P2 cosine theta instead of 3 halves cosine squared theta minus 1/2 plus 1/2. But this is a good enough final answer. So if you reported this to somebody, they would know what all of these things are. So B naught, what you told them, and then P naught and P2, anybody who's anybody knows what the second and 0th Legendre polynomials are. So this is a good enough answer. And small little typo there, that should be R cubed.